What if you could capture a puff of air and make the world a better place? As the delicate balance of our planet teeters on the brink of irreversible climate change, carbon removal technologies offer a glimmer of hope. Yes, we should always prioritize emission reductions. But entities like the International Energy Agency, UN Environmental Programme, and the World Resources Institute have all recognized that carbon dioxide removal, or CDR for short, will be essential. Some estimates put our needs at the billion-ton scale by mid-century. Today, we delve into the complex world of these technologies, providing an overview of their potential, their pitfalls, and their promise. In the realm carbon dioxide removal, we have a broad spectrum of options. Each comes with its unique set of advantages and challenges. Starting on the lower end of the cost spectrum, we find afforestation and reforestation. These nature-based solutions are not just cost-effective, but, if done properly, also offer a host of co-benefits like biodiversity, conservation, and soil erosion control. However, their scalability remains limited due to competing land use demands, and although in theory the carbon they absorb has the potential to be sequestered for centuries, a single wildfire can release all of it. There is therefore no guarantee of permanence when it comes to afforestation and reforestation. Soil carbon sequestration, another nature-based solution, also falls in the cost-effective category. It can also be referred to as carbon farming or regenerative agriculture, and it consists of various ways of managing land, especially farmland, so that soils absorb and hold more carbon. It enriches our soils, enhancing agricultural productivity while capturing carbon. But measuring, reporting, and verifying the actual amount of carbon sequestered poses a significant challenge. Biochar, a charcoal-like substance, presents another intriguing option. Biochar is a natural charcoal created from organic materials like wood chips and agriculture byproducts, using a process called pyrolysis. As plants grow, they absorb and store CO2, but upon decay they release it back into the environment. Biochar disrupts this cycle, therefore being capable of realizing a carbon-negative process. Biochar can also help improve soil fertility and water retention, increasing agricultural output, efficiency, and resiliency. However, its production process can be energy-intensive, which is especially problematic if it's produced with fossil fuels, and its broader environmental impacts are still under study. Direct air capture and storage, the most futuristic and expensive of our options, literally sucks carbon dioxide out of the air and stores it. Today, direct air capture costs can exceed $600 per metric ton of CO2. Although these costs are starting to come down, the International Energy Agency forecasts that with more widespread deployment and innovation costs could fall to $100 per metric ton in the near future. It's a promising technology, but its high energy requirements and current costs make it a challenging proposition today. Terrestrial enhanced weathering, which speeds up natural processes to store carbon in rock, is a fascinating concept. It works by spreading finely ground silicate rock such as basalt onto surfaces. This speeds up chemical reactions between rocks, water, and air, removing carbon dioxide from the atmosphere as it does so. However, enhanced weathering by itself would require enormous amounts of rock, and before being applied on large scales requires additional research to evaluate the rates at which weathering occurs and consider potential side effects. Most of Earth's terrestrial carbon stocks are held in peatlands and coastal wetlands, for example mangroves, tidal marshes, seagrasses. The carbon stored here is known as blue carbon. First, we need to do everything we can to keep existing stocks healthy, but restoring and expanding them is also an affordable solution with excellent carbon storage potential, with some cost estimates coming in as low as $10 to $100 per metric ton of carbon. However, there are, of course, limitations. Some wetlands emit potent non-CO2 greenhouse gases, such as methane, which can offset the climate benefits of carbon removal. Carbon would also be released if these ecosystems are degraded, requiring careful management indefinitely. The monitoring and verification of these solutions is also difficult and costly. Ocean alkalinity enhancement, still in its infancy, aims to increase the ocean's capacity to absorb carbon. It works by adding alkaline minerals to seawater to enhance the ocean's natural carbon sink. Our oceans already hold around 38,000 gigatons of carbon, 16 times more than the terrestrial biosphere. In terms of practicality, their ability to store additional carbon is virtually boundless. But there are concerns, including significant energy use and mining requirements, and unknown potential consequences on marine ecosystems. So, as we can see, the world of carbon capture and removal technologies is as diverse as it is complex. Each option has its strengths and weaknesses. Some are cheap but hard to scale up. Others offer massive potential but come with hefty price tags, and some are still too new to fully understand or to reliably measure. In summary, there's no silver bullet solution to our carbon problem. Each technology plays a role in our fight against climate change. The challenge lies in finding the right mix of methods, developing them responsibly, and implementing them effectively. As we journey into a future fraught with uncertainty, these technologies offer a beacon of hope. They are the tools we have to mend the world, one captured puff of air at a time.